In this video, we will discuss, finish our example, right? Last time, we have a region which is bounded by y equal to x squared, and above the line segment 0, 1, right? Get such a S, right? S is a shaded region here, bounded by y equal to x squared, x equal to 1, y equal to 0, right? So we know that by our discussion, we know that the area of S is defined to be as n goes to infinity, Rn. I recall that Rn here is divide your region into smaller stripes. Rn here is a rectangle formed by the right endpoints, right? If you have area exists, this limit has to be a finite number. Then doesn't matter which endpoint you choose, either left or right, you get same number, right? And so this is basically we have our discussion. So this is n goes to infinity summation 1 over n I over n square I from 1 to n here, right? Now let's try to evaluate this limit, right? Because you can see that in this limit, as n getting bigger and bigger, the term here is getting bigger and bigger. We don't have any good way to handle that. So our only way here is try to write this sum as a function of n. Then we can apply L'Hopital's rule or the limit techniques we have learned so far to evaluate that, right? So let's try to simplify our summation first. I from 1 to n here. 1 over n, I over n squared, right? Now you can see that as I changes, this is summation about I, right? Now you can see that this summation, this term compared to the summation is a constant, because as I change, 1 over n doesn't change, right? So this is bring out all the common factors. I from 1 to n, 1 over n cubed times I squared, right? This is 1 over n cubed summation I from 1 to n here, I squared. We have discussed this finite sum of natural number square, right? That is given by recall that summation I from 1 to n here, I squared, is n times n plus 1 times 2n plus 1 over 6, right? That's one fact. We didn't prove it, but you can use mathematical induction to prove it, right? You can prove the basic step, then do the inductive proof. So this equal to 1 over n cubed times n plus 1, 2n plus 1 over 6. Okay, now we are ready to evaluate the area, right? Because we simplified the sum as a function of n. As n getting bigger and bigger, this is basically a fraction, right? As n getting bigger and bigger, you get infinity over infinity, right? So the area of the region S we are interested is as n goes to infinity, n times n plus 1, 2n plus 1 over 6, 6n cubed. So this is infinity over infinity, right? Apply L'Hopital's rule. Maybe 3 times, you can do that 3 times. You get, this is 1 over 3. So the area of the region bounded by y equal to x squared is 1/3, right? So another notation for such an area is this is basically equal to the integration x is changing from 1 to 0 to 1. The function above is x squared dx. So this is how do we define the integral. And one application of integral is this help us to evaluate some area of region if you are given a non-negative function and also a finite and bounded region, finite bounded interval or range, you get a finite region, you can evaluate the area using integral. So that's one application, which is also a motivation of the second, third, actually, key definition in calculus, integral.